SwayamPrabha. Digital India. Educated India.
Today onwards, we are going to talk about the continuum problems, in the sense that the body, the material is continuously distributed over the problem domain. So these are actually the real applications of finite elements. And typically, if you talk about the three-dimensional bodies, so such as the dams here. So some typical examples of these 3D problems are typically a dam with some loads here. So this is, as you can see, that this dam is a three-dimensional body, and the matter is continuously distributed over the domain, a three-dimensional domain, which is of our interest. Something like if there is some typical water here on one side, and then there is another load, the traffic load on the dam, and typically how you want to find out the deformations, and followed by the stresses and strains, which are of primary importance. So these so this is a three-dimensional body, and we call it as a continuum body because over this domain, the material is continuously distributed. Not only the material, but the deformations as well as the stresses and strains are completely the functions of x, y, and z. So like this, so this is a typical problem from civil engineering. On the other hand, we also have something like say this is another typical application. So this is a typical plate, maybe of certain thickness, and maybe with some hole. So the plate overall is a rectangular domain, but with some hole here. And if it is subjected to certain forces on the outer boundary, so what kind of deformations it has and what kind of stresses and strains have. So this typically again is a three-dimensional body. So like this, we have many examples. Like in mechanical engineering, we have many automobile parts. For example, we have pistons, engine block, connecting rod, crank, walls, tires, and the body. They are all typically three-dimensional body in nature, and which are continuous in this sense. So this is in contrast with what we have talked about or studied until yesterday, the discrete structures. So in the sense that typically a bridge structure where it can be discretized into a smaller elements, and like one-dimensional truss elements or one-dimensional beam elements, which can be analyzed, or where the equilibrium equations or the governing equations for each element can be written down in a very easy manner, and which can be assembled. So this is what we have seen. But then here, when we talk about these kind of continuum problems, where the geometry as well as other variables of interest, they are all continuous functions of say x, y, and z. So for example here, so this is x, y, and z axis. So here also we have maybe x and y and z. So here every point here, P is a typical point, and then where the deformations are functions of x, y, and P is a typical point. So that means that the total solution will consist of all these points of P similar to P, and that's what we want to get. So here, as I was saying, that these things are not so easily clear. So how to disguise this, how to kind of make it into smaller elements where we can write down the governing or equilibrium equations for each element, and then on and on, how to assemble, and those are the typical things. And so these are actually the typical problems of engineering, either civil or mechanical. So where the application of finite element is very much required. So these are very complex problems, both from the geometry point of view as well as from the variables which are of our interest here. So here the variable of interest are typically the deformations of each point. And so you can even say that these are static problems. So static problems, that means that the deformations are not functions of time or steady state, or they can even be functions of time if they are typically subjected to time varying forces, like the dam may be subjected to seismic vibrations, or even this one can be subjected to forces which are functions of time. So typically the variables of interest here are functions of x, y, and z, 3 dimensions in nature, and then maybe functions of time if they are transient or dynamic in nature. So what we are trying to do now is that we are going to see several applications, and then we are going to see how finite element equations can be developed for each of these typical applications. So in reality, so what we have is that we have a physical problem, and then there is a object or which is occupying some space, which we call as the domain. So in that domain, so there are certain governing equations that are defined typical of that problem, together with the boundary conditions. So there is a boundary, and together with on the boundary, so since it's going to interact with the other bodies, so then since you are isolating this one, then we have to apply certain boundary conditions. So that is typically the domain. But then within the domain, we have governing equations. So these governing equations may be in the form of differential equation, and so any variable or any function which satisfy this governing equation and the typical boundary conditions will be the solution. So if it is exact, it is fine, but on the other hand, we cannot have exact solutions for these typical problems. These are all very, very difficult and very complex in nature. So we are going to aim at the approximate solutions. So what we do here is that today, so we are going to concentrate on what are the governing equations, what is the domain, what are the boundary conditions of some typical problems. And many of you might know it, but for the sake of completeness, so I'm going to derive a few one-dimensional, two-dimensional, and three-dimensional governing equations for some typical problems. And so as you can see here, so the one dimension and two dimension and three dimension, you might be wondering, the typical bodies, are they really one dimensional? So that means that are they only in the as a line, only either in the x direction or y direction? No, it is a mathematical simplification where the variables of interest are only functions of x, okay, only one x. So that means that the other two dimensions, y and z, are there definitely, but the variables are not, or functions of y and z. Now let's look at, there are many problems which we come across, something like solid mechanics problems. Solid mechanics problems, or even, in fact, the beauty of finite elements is that the methodology can be applied to many fields. So it can be solid mechanics, where we have a body subjected to forces and we would like to find out the deformations, strains and stresses. Or on the other hand, the finite elements can also be applied to other fields like heat conduction, where we talk about the temperature, and of course it has a conductivity, and the temperature will be a function of space variables x, y, and maybe z, depending upon 1, 2, or 3 dimensions. So, and then very similar equations can also be derived for many other problems like torsion, many other problems like seepage or groundwater flow, or deflection of membranes, or even strings. Okay, so we will see some of these governing equations. We also see what are the boundary conditions that need to be applied. Okay, so in fact, I can also tell you a little bit about, the problems can be defined in terms of differential equations. Okay, where you see maybe the total differentials or partial differentials, so depending upon the type of problem. Or problems can also be defined mathematically in terms of other approaches like variational problems, variation of certain quantity. Or they can also be defined in terms of the virtual work principles, such as which is quite common in the case of structural mechanics. So there are 3 typical ways of defining the problems, either in the form of differential equation, which I'm going to just tell you in detail, or it can be in the form of certain variational principle, or thirdly, it can be in the form of certain virtual work principle. So we will see all of them. So typically, to start with, we will just try to derive some typical governing equations for some of the problems. So in solid mechanics, so we have, as I said here, there are many one-dimensional problems, two-dimensional problems, and three-dimensional problems, and similarly even the heat conduction problem. So why we take these things, in fact, many times we even prefer to deal with heat conduction problem. This is because here in solid mechanics, in say for example 2 dimensions, there are the deformations in x direction, deformation in y direction. So that means that there are 2 variables which we need to find out. Whereas in the case of heat conduction problem, though it is 2-dimensional geometrically, but then the temperature is only functions of x, y, and so then there is only one variable of interest, that is the temperature. So that way, the heat condition problems, we concentrate more on this type of problems because they are easy to handle. Okay, all right. In the solid mechanics problems, let us just look at, to start with, just one dimension problem. So one dimensional solid mechanics problem. So as I was telling, maybe for the just sake of here, the deformations 1D, 2D, and 3D. Here the deformations are, for the sake of completeness, so deformation are only in the x direction. So you call it as a function of x, y. So similarly in 2D, you have 2 variables, u and v, and each one of them is functions of xy. And in 3D, we have 3 variables, so 3 deformation components. Each one of them is functions of x, y, z. So like this, so these are the deformations. And in heat condition, so again, it can be 1D, 2D, so here. So we have only the temperature, which typically we represent by the letter phi. Phi may be function of x, y, and z. So that is what typically the problems are. And let's try to 1D solid mechanics problem, where the body is essentially in the form of one dimension, not necessarily the other 2 dimensions are, as I said, are negligible or not, or of small dimensions. So let's look at here. A typical problem of so this is a rod of variable cross section, one dimensional rod, thin rod of course, but the other cross sectional area is not negligible. It is some small value, however, and then we have a force is acting in the axial direction, and then here what is the variable which is of interest is the axial deformation. So the axial displacement, say for a typical point P here, axial displacement at a P, we can write it as u, and then here we write it only as a function of x. This is because the assumption that the whole cross section here is small, thin, and then every point in this cross section will have a displacement in the x direction, same value. It is a uniform displacement in the x direction, which is given by u. Obviously, it is a function of x. So that means that if you measure x here from this fixed point, and then this x is the distance to any typical point here, and then the displacement here of this point P is given by u, which is a function of x, right? So this is a one-dimensional thing, because and of course here we are also making an assumption that the material is same, or we can even slightly generalize, the material is the same in the cross section. So that means that there is no change in the material over the cross section. It may change. For example, this may be made of 2 materials. In the first half you may have one material, in the second half you have another material, but however at each cross section it is the same material. So that's, in fact, you can easily handle, and in fact that is the power of FEM. So even the material changes from point to point, not in a very microscopically, but definitely if it changes, so finite elements can handle. So if you have this kind of very typical problem, which is the one-dimensional in nature, and then if you want to draw what is the equation here, governing equation, how to define. In fact, here the domain of the problem is x varies from 0 to L. So the domain is x varies from 0 to L. So that means that the x is equal to 0 and x is equal to L are the endpoints or the boundary points, and our domain of interest is between 0 to L. And then this is being acted upon by f here, and let's typically look at a typical delta x here. So we want to look at the governing equation. So we are looking at the equilibrium of this one, where since it is a small, this element delta x here is isolated, and then there's a force acting on this direction, on this small boundary, and then there's another f here. But obviously this f is not the same as this one. It may be different from, in fact, f is a function of x. So this isolated free body diagram here, which is the internal force, but now acting as an external force here, is a function of x. So in fact, this can also be written as f df by dx into delta x, right? So it is also how it is written in the calculus terminology. So, and then what else is that? So not only this f, we can also assume that there are forces here, a distributed forces q, which are so q is a distributed which is q, and it may be function of x. It may be constant or it may be function of x in general. So you can see here q is in fact, though it may be distributed all over the surface, we can assume that it's only being shown in the x direction, typically on the axis. So what we have here, if this is the small element which is under equilibrium, and so this is under the action of force F here, and then there is a force, distributed force Q, and then there is on the right side of the face we have F plus delta F, or F plus df by dx into delta x. So this is what it is, and then if you write the equilibrium, so this is minus F, and here we have F plus df by dx into delta x, and we have here Q multiplied by delta x. So this is equal to 0, and you can cancel F here, and then you have df by dx, and delta x you can also cancel, and this is the equation df by dx. So, but this is still in terms of f here, and then what is that? Our primary variable here is this one, u, the displacement. So we should be able to convert this into a displacement. So if you recall, the internal force here, F, the internal force F here is sigma times A. So sigma is the stress. Okay, sigma is the, if you call it as a distributed stress like this one, and sigma multiplied by the cross-sectional area A here, sigma is the stress. And this stress, we can write it as, in terms of strain, as E times epsilon. Epsilon is the strain times A. And further, what is the strain? So strain is a rate of change of deformation. So that is, how do we write it? So epsilon is nothing but du by dx times A, right? So the strain can be written as du by dx at any typical point. So this is E du by dx times A. So this is what F is. And then if you substitute that in the above equation, in the equilibrium equation above, so what we can get, so substituting that in the above equation, in the above, so what we get here, df by dx, so that means that d dx of E du by dx times dx times A plus Q is equal to 0. So depending, it's the interesting part, d dx of AE du by dx, you can write it that way, and times du by dx. So interestingly, so this is a very generalized equation in the sense that if E, the Young's modulus of the material, is also a function of x, so then you can differentiate it this one, or A also can be function of x, and you can also take that into things. So you can just write this one if you want, A and E, if they are constant, you can write it like this. If A and E are constant. Otherwise, you can leave them inside the bracket. So, okay. So, this is the now, d square u by dx square, this of u. So, this is the typical equation. So, this is valid everywhere between 0 to L. So this is the domain, 0 to L is our domain, and where you have the governing equation. So this governing differential equation is supposed to be satisfied, and each and every point x between 0 to L. So this is the governing differential equation, and then we also have something more known as the boundary conditions. So no problem is complete without defining boundary conditions. So that's the boundary is what? X is equal to 0 and x is equal to L. So these are the boundary conditions, and then we have to specify what is happening here. So at x is equal to 0, for example, in this particular problem, at x is equal to 0, it's fixed to the fixed wall. So that means that at x is equal to 0, so this cross section here will not undergo any deformations. There is no deformations. So that means that here, so at x is equal to 0, we have u is equal to 0, right? And what about at x is equal to L? So where in addition to Q here, which is distributed all over, we also have an additional force F. So what is F here? So F is a force which is applied on this end. So how is this F related? So F is nothing but the cross-sectional area of at x is equal to L multiplied by the stress, right? And so this is stress at x is equal to L. So we can also write this one, sigma is nothing but E times du by dx, or if you want, E times epsilon at x is equal to L, right? And which we can write as AE du by dx x at x is equal to L. Understand? So that means that there are two boundary conditions. At x is equal to 0, we have the deformation u is equal to 0. At x is equal to L, we have an applied concentrated force F, so which should be related to the stress at that point. So the stress multiplied by the cross-sectional area should be equal to the force, but then this stress is evaluated at x is equal to L, and which can be converted into the basic primary variable u in this manner, and sigma is nothing but E times epsilon at x is equal to L, and epsilon is du by dx, so AE du by dx. So that means that the derivative of the displacement at x is equal to L multiplied by AE should be equal to the externally applied forces. So this is in the form of displacement itself here, the boundary conditions, whereas this is in the form of derivative boundary condition. So these are also very, very important for us. So sometimes we'll give the boundary conditions in terms of the variable itself. Sometimes we give it in terms of the derivative of the variable. And so these are all very typical, which we encounter often. So I think I'll stop here. We'll continue with the 2D problems in our next class. Bye-bye.